Sections 4.1 and 4.2 involve a lot of the standards that we've dealt with earlier on in the school year, but we're readdressing them and going further and more in depth into them, so we're getting a deeper understanding of what bonding is. So if we want to think back, what bonds two atoms together, it would be the valence electrons. We know that the inner electrons are too far in, they are not going to be involved in bonding, and we know that the octet rule is a good rule of thumb, but it's not what is actually being used to create the electrostatic interaction between either cations and anions or electrons that are being shared and their cation remains of their nucleus. We've got three general types of bonds. We've talked about two so far, ionic and covalent, but covalent can actually be split into two other types of bonds, pure covalent and polar covalent. So we're going to talk about all three of those in the notes today, starting out with ionic. So, ionic bonds are when two atoms exchange valence electrons, forming ions. They exchange so that they may be in the same isoelectronic series of the nearest noble gas. So we're thinking electron configurations here. And we look at how they either gain or lose electrons in the easiest way possible to be like the nearest noble gas. So we think back, what is an anion? Well, an anion is an ion that has a negative charge, a negative ion, because it gains electrons. Electrons are negative and would be a nonmetal. Those nonmetals are closer to the noble gases, so they'll gain rather than lose electrons. So we think to our electron configurations, and we'll take a look at our periodic table to write the electron configurations of these and identify what they would do. So first of all, beryllium is 1s2, 2s2. It has 4 protons and 4 electrons in the atom. Fluorine, I've got a typo here. It's 1s2, 2s2, 2p5. It should be a 5 right there, so don't do a 6, write a 5. 2p5. What I do have written there is the electron configuration for the noble gas that it becomes. So looking back at beryllium, beryllium is much closer to the 1s2 helium than it is to neon, which would have a 2p6 here. I'd have to gain 6 electrons. That's too difficult for beryllium to do. It would rather lose these two that aren't held on very tightly due to our atomic radius and electronegativity. And so it's going to lose those two to be like helium, while fluorine becomes what I accidentally have written down here already, 2p6, which is like neon. So when it does that, we've got those 2 electrons going away, 1 getting added here. We get Be2 plus. That's because beryllium started out with those 4 protons. It still has those 4 protons, but the 4 electrons it had before, it now only has 2. So I have a 4 plus and a 2 negative. That gives me a 2 plus overall. I have 2 more protons than I have electrons. Now the fluorine has gained 1 electron. It had 9 protons to start with. It now has 10 electrons, so it's 9 minus 10 gives me a negative 1 overall. And we just refresh ourselves on what those would be. I've got a cation when I have a positive charge and an anion when I have a negative charge. Now, I'm going to add 2 new words for us. So the first word is oxidized. When I lose electrons, it is said to be oxidized. Oxidation is the loss of electrons. When I gain electrons, it is said to be reduced. Now when we get into chapter 9, we're going to be dealing with oxidation and reduction, or redox reactions, in depth. At this point, it will benefit you to just memorize that oxidation is losing electrons and reducing is gaining electrons. That's going to help you out a lot when we get to chapter 9. So memorize them now. Now ionic bonds, continuing on, they're going to form between elements that have very different tendencies to lose electrons. So thinking back to what this means with our periodic trends, we're thinking about electronegativity, and greatly differing tendencies would be our metals and our nonmetals. So we've got A as our answer here. Okay, we've got electronegativity differences between metals and nonmetals is what makes an ionic bond. So a little reminder for us on electronegativity. Electronegativity is the ability of an atom in a molecule to attract electrons to itself. The higher the electronegativity, the stronger the pull that atom has on an electron. You can either rip it away or just pull partially depending on what the electronegativity difference is. We've got a nice image, kind of 3D image there of electronegativity values. In your note packet you have a much better version. It's the one from IB. And so we're going to use this to do some comparisons to identify what type of bond will form. So first of all, we need to remember what difference stands for. Mathematically, what does difference stand for? Well, it means subtraction. So what I'm going to be doing is a bunch of subtraction between those electronegativity values, like 2.5 minus 2, I would get 0.5. I always do the bigger number first, the lower number second. I subtract the lower number from the bigger number, and we get a value, and those values can be used to identify what type of bond we have. So this is a beautiful chart for us. If I have zero difference, so if my two values are the same, I would have pure covalent. Now these would definitely always be my diatomic molecules, my magical 7. Those would be pure covalent. And then we have other ones as well. So if I look at my chart and I take selenium at 2.5 and bond it with carbon at 2.5, the difference would be 0. So that bond between carbon and selenium would be a pure covalent bond. Now if I have a 1.8 or greater value, I have an ionic bond. So we can look back at our chart. We've got a 1.0 there. We've got a 3.5 there. 3.5 minus 1.0 gives me a 2.5. That's definitely greater than 1.8. I would have an ionic bond. Anywhere in between those values, so 0 and 1.8, is called polar covalent. So they are sharing electrons, but very unequally, and we're going to talk more about that definition later. So one of them has a greater electronegativity value, but not great enough to pull them into full ions, where one of them has the electrons around it all of the time. So let's take a look at our chart. We have manganese and nitrogen. When we find these two on our electronegativity value chart, and we take those electronegativity values and subtract them, we get a value of 1.4. So manganese and nitrogen, even though I have a metal and a nonmetal, would actually be polar covalent because they'd be sharing the electrons slightly, with nitrogen holding on to the electron more of the time and with more energy than the manganese. Now if we had oxygen and aluminum, and I look at those two values on my electronegativity chart and I subtract them, I find that I get a difference of 1.8. So that means that I have an ionic compound. Ionic bonds are when oppositely charged ions attract due to electrostatic forces to form electrically neutral compounds. It is not normally two atoms bonding in isolation. Think of our table salt. Crystals of table salt. That's not just two atoms. I couldn't look and see my table salt if there was just one atom of Na and one atom of Cl. Okay, so these are multiple Nas and Cls bonded together in a 3D ionic lattice or crystalline structure. And this crystalline structure, it is rigid, it is nice and organized, it has a fixed arrangement of a repeating unit. And so if I were to slice apart my NaCl, it's going to have the same setup, the same general basic structure all the way through. And now we remember back to when we started doing naming, and we identify that we had always the smallest ratio of ions. Makes a lot of sense. I wouldn't want to take my one crystal of NaCl, my table salt, from my table, use an electron scanning microscope to identify and start counting out ions of Na and Cl and get something like Na1000 and Cl1000. I wouldn't want to do that because one, two different crystals of salt are going to have a different number in them, and two, that would take an inordinate amount of time. So what we always do is write the smallest ratio of the ions that would be present. And the way that we did that before was look at the ions and crisscross those charges to figure out how it would be electrically neutral. So if I took magnesium, which is a 2+, look at that on the periodic table, magnesium is a 2+, and oxygen is a 2-. When I would crisscross those, I would get 1 magnesium for every 1 oxygen because the 2's would cancel out. I'd have MgO. So I always write the smallest ratio of those ions rather than a greater number, or by counting the amount of ions that are present. A crystalline structure can look like this. There's different general shapes, and if you get into a material science class, you're going to learn what those different shapes are, or what the different patterns are. So some properties of ionic compounds. It's not only important to memorize these statements, but it's more important to understand why they happen. So the volatility of ionic compounds, or the tendency of ionic compounds to vaporize, is very low, and that is because of that fixed crystalline repeating structure that has so much pattern to it. It's not going to start randomly just letting off vapors of Na and Cl, or whatever the ionic compound is. It's too nice and rigid to be able to do that. We also have electrical conductivity, that is the ability to conduct electricity, and that is very low when we have a solid. Again, because of that rigid pattern of structure. Even though I have cations and anions, so pluses and negatives, they are in a fixed position, so there is no way for the electrons to be moving through there in a nice way. As a liquid, however, so if I heat it up with enough energy, and it takes a lot of energy to get an ionic compound to get into the liquid phase or to melt, that could work because those cations and anions are then free to move around. They're not in that fixed, rigid state anymore. Or if I took my table salt or my other ionic compound and dissolved it in an aqueous solution, now I have ions again free to move. They're not stuck in the rigid crystalline shape anymore. So in that instance, they would also be able to conduct electricity. Ionic compounds are very soluble in water and other polar solvents, and we're going to learn more about that when we learn about intermolecular forces in a few standards from now. And then finally, the melting point and boiling point are high because those cations and anions are held so tightly together because their charges are exactly opposite in that nice rigid structure. Now on to covalent bonds. I said that there's two types, but both types are formed by the electrostatic attraction between shared pairs of electrons and their positive nuclei. So I still have electrostatic attractions, but this time rather than a cation and an anion, the electrons that are being shared are pulling in those positive nuclei. There are not just polar covalent and pure covalent, but within polar and pure covalent, I can have either single, double, or triple bonds, and those depend on how many electrons are shared. So the single bond is sharing 2 electrons. This is my longest of the bonds, and it is the weakest of them because they're only sharing 2. The more electrons I share, though, the shorter I get and the stronger it is, or the harder it is to break apart that bond. So a double bond is sharing 4 electrons. It is shorter than a single bond and it is stronger than a single bond. But triple bonds are my strongest and shortest yet, sharing 6 valence electrons. Now pure covalent bonds are going to share their valence electrons equally. So these are the ones that have the same electronegativity values. They're between nonmetals with the same electronegativity values. I just repeated myself. Very important fact, so we don't want to forget it. Then I've got polar covalent bonds that are unequally sharing their valence electrons. There's a small difference between electronegativity values, so greater than 0 but less than 1.8. And so one of the atoms is sharing, or feeling the effects of the electrons that are shared more than the other one. So one of them is partially positive, one is partially negative. This often creates what is called a dipole, which is a center of positive charge and a negative charge. So what does that mean? How do we represent these partial charges? So let's look at HCl, hydrogen chloride or hydrochloric acid. We want to look at our electronegativity chart to identify which one is more electronegative. And when you do that, you'll see that chlorine is more electronegative. It wants the shared electrons more. So it is going to pull that shared electron from the hydrogen to the chlorine more of the time. They're both sharing it, but not equally. The hydrogen gets it much less than the chlorine. So the chlorine has one more negative around it more of the time. So that means that the shared electron pair will be pulled to the chlorine more of the time, making it partially negative. And the hydrogen then is partially positive because it doesn't have that electron around it most of the time. And we represent it in one of two ways. I could either use these nice Greek deltas, which represent partial as a positive or partial as a negative, to tell me which of the atoms are partially positive and which are partially negative. So I said that the chlorine has the electron around it more of the time, so it would be my partially negative. My hydrogen, on the other hand, does not feel the effect of it as often, so it is partially positive. My other way to represent this would be that dipole, and this is where I've got a plus. You can kind of see a plus above the hydrogen, and then a little arrow showing that the electrons are moving towards the chlorine more of the time.